Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into the fascinating world of transmission lines and the pivotal role Oliver Heaviside played in their understanding. Get ready for some electrifying insights.
I'm buzzing with anticipation. So, Heaviside, what's the big deal? Was he just some 19th century cable guy?
Oh, far from it. Heaviside was a self-taught genius, a true maverick who revolutionized our understanding of electromagnetism. He started as a telegraph operator, noticing something peculiar about submarine cables. When water leaked in, causing short circuits, the signals became clearer, less distorted. This observation, seemingly simple, sparked a revolution.
Interesting. So what was the prevailing understanding of transmission lines back then? Was it just, wire?
Exactly. Electrical engineering was in its infancy. They could build telegraphs, but long-distance transmission was a mess. William Thomson, later Lord Kelvin, had a model, but it was incomplete. He only considered resistance and capacitance, missing a crucial element.
And that element was
inductance. Heaviside realized that inductance played a vital role. He incorporated it into his model, showing how it affects signal propagation. His model, unlike Thomson's, accurately predicted the behavior of signals in long cables.
So Heaviside's model was more accurate? How did he do it? Did he use some fancy math?
He certainly did. He took Maxwell's 20 equations and distilled them into 4, the ones we all know and love today. He also brilliantly visualized the transmission line as a series of inductors and capacitors, showing how signals propagate as waves. He even calculated the characteristic impedance, a crucial parameter for matching transmission lines and preventing signal reflections.
Characteristic impedance. So, that's why we need to match impedances in our antenna systems, right? To avoid reflections and signal loss?
Precisely. Heaviside's work laid the foundation for this understanding. He showed that the impedance is determined by the inductance and capacitance per unit length of the cable, L/C. If you terminate the line with a resistor equal to its characteristic impedance, you get perfect signal transmission, no reflections.
Amazing! But what about the speed of the signal? Can we make signals travel faster than light?
That's a great question. The speed, as Heaviside showed, is 1 square root LC. But there's a catch. While we can adjust L and C, we can't make the speed exceed the speed of light. Changing the cable's geometry affects both L and C in a way that keeps the speed below the speed of light. Even with a coaxial cable, changing the conductor's thickness affects both inductance and capacitance, preventing superluminal speeds.
I see. So it's all about the interplay between inductance and capacitance. But what about signal loss and distortion? Real-world cables aren't perfect, right?
Right. Heaviside also tackled loss and distortion. He incorporated resistance and leakage conductance into his model, showing that these factors not only attenuate the signal, but also distort it. He found a condition for distortionless transmission. L/R equals C/G. This means the ratio of inductance to resistance must equal the ratio of capacitance to conductance.
So how do we achieve distortionless transmission? Is it just about using better materials?
Well, we can try to decrease resistance by using thicker copper, or decrease capacitance by increasing the distance between conductors. But often, the most practical solution is to increase inductance. Heaviside suggested adding coils at intervals along the cable, a technique later patented by Pupin and used extensively in telephone lines.
Pupin coils. So should we be adding these to our antenna cables? To improve signal quality?
Not really. For narrowband signals, the distortion is usually negligible, and those coils would act as a low-pass filter, blocking high frequencies. Heaviside's work is more relevant for understanding the fundamental principles of transmission lines, not necessarily for tweaking our antenna setups.
Got it. So Heaviside's legacy is far-reaching. He wasn't just a telegraph operator. He was a foundational figure in electrical engineering, a true unsung hero.
Absolutely. A self-taught genius who transformed our understanding of electromagnetism and transmission lines. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into the world of Oliver Heaviside and his groundbreaking contributions. Until next time, goodbye.
Bye-bye.